Okay, hello, good morning, class. Right. So today we continue, okay, to the last subtopic in chapter 3, okay, and then we will discuss about your test, okay, and let's see whether you can understand or not is what is actually the question one, okay, for the PBD test for this one, the one that you took on Thursday, I think. Okay, so we discuss one by one. Alright, so we move on to the next last subtopic, okay, on this chapter. Okay, so man-made satellites, right? So the International Space Station (ISS) can be seen, okay, from the Earth because of its large size, and also the orbit is at the height of 498 kilometer. Okay. Bermiasat satellite is difficult to be seen, okay, because of its small size and also the orbit at the height of 35,786 kilometers. So it's quite further if you compare with the ISS, right? So that's why it's hard for you to see the Miasat satellite. Okay, and the satellite can move in orbit at a specific height and also in the suitable linear speed. Right, so the activity one, you have to determine the linear speed of the satellite. So figure below shows the orbit of a satellite around the Earth. So a satellite moving in a circular orbit, right, around the Earth experience a centripetal force. Okay, so this one we already learned, right? So let's say there's an object, right, that rotate, okay, around, let's say this is a planet, right? So the planet rotate around the Earth, so there will be a centripetal force, right? And the centripetal force is actually equals to the gravitational force, okay? So the equation that we can make here, okay, that I already explained just now, the gravitational force, okay, is actually equals to the centripetal force. So the gravitational force is acting, right, between these two objects. So this one, the Earth, and also the satellite. Okay, and then the centripetal force is acting towards the center of the object. So means it's acting towards the Earth. Okay, so we can make the formula, we can equate the formula that F is equals to GMM, all right, over R squared. So this is the formula for the gravitational force, right, and equals to the centripetal force, that is F is equals to mv square R. Okay, so when we equate the equation, okay, so this one we can just cancel it. Okay, so it will be left by gm r square over v square over r. Okay, and then you just cross multiply. Okay, so v square r, right? So this one also v square with v square r square. Okay, right, so this one also we can cancel it. Okay, so this one will be left with only one r. Okay, so gm is equals to v square r. Okay, this is the equation, right? And then after that, okay, from that, v square is actually gm over r. So if you want to find the linear speed, okay, the linear speed of the satellite means what is the speed of the satellite, this v, okay, this value of v. Okay, so you just, this one you need to square root the formula. Okay, so this is the formula for the linear speed of the satellite. Okay, so we derive from that. Okay, so gm is a constant. Okay, so g we already know is actually the constant for the gravitational value, right? That is 6.67 times 10 power of negative 11. Okay, and the m is the mass of the Earth, right? And r is actually the radius. Okay, so let's say this is the Earth, okay, and this is the satellite. Okay, so this is the radius of the earth, okay, the capital letter R. While this one, okay, the height of the satellite from here, from the surface of the earth to the satellite, this is h. Okay, so if you want to find the linear speed of the satellite, okay, so you need to add the radius with the height of the satellite from the surface of the earth. Okay, so that's why R plus H. You just take R means the object is on the surface of the earth. But for the satellite, you know it's at the outer space, right? So means you have to consider the height of the satellite from the surface of the earth. So R plus H. Okay. So this is the formula for the linear speed of the satellite. Okay, any question you want to ask teacher before I continue? Are you clear? How do we derive the formula for the linear speed? Okay. All right. So what is the requirement so that a man-made satellite can be launched to keep orbiting at specific height around the Earth at radius orbit r? Okay, so what is the requirement? So the requirement is the linear speed of the satellite. So you have to know the linear speed of the satellite. So to make sure that it keep orbiting in the same orbit, okay, and it will not collide with the other satellite. Okay, and also it will keep rotate in the specific height. Okay, so what we need, you need to know the linear speed here. Okay, so can you calculate this one by using the formula here? V is equals to gm over r, right? And square root. Okay, but this one r is actually the r plus h. Okay, monitor, can you check who's absent? I think one person is absent here, right? 'Did you get the answer? 2001. Yang does. Oh, okay. She already told me that he needs to go to the funeral. Okay, so 2178.56. Okay, thank you, Sylvan. Sylvan. Thank you. Okay, so that's your answer. So anyone got other answer from 2178.6 0.56 meter per second? So means if the answer is correct, so means the satellite, the linear speed of the satellite, okay, when you move right around the Earth, so the speed will be 2178.56. So let's check whether your answer is correct or not. Wait. Okay, so maybe we have to calculate it. Okay, so let's me take my calculator first. Okay, so the formula is V is equals to G M, okay, R plus H. Okay, so the value of G is 6.67 times 10 power of negative 11. Okay, and the mass of the earth is 5.97 times 10 power of 24. Okay, and then divide by r is actually the radius of the earth, that is 6.37 times 10 power of 7. Okay, but this one is only the radius of the earth, only this one, so you have to add the h here. Okay, the height of the satellite, there is 20,200 kilometer. Okay, so this one you have to change the unit to meter. Okay, so I just change to 20,200. Kilo is 10 power of 3. Okay, so if you just multiply by 1,000 also can, right? If you want to change to meter, you have to change to meter because the radius of the earth is in meter. Okay, so next you have to calculate. Okay, so 6.67 exponent negative 11, okay, times 4.97, okay, exponent 24. Okay, so you got the answer 3.982 times 10 power of 14. Okay, and then you add the radius there with the height of the satellite. So 6.37, okay, exponent 7 plus 20,200, okay, exponent 3. So you got this one. So 3.982 exponent 14 divide by answer. So you got this one. Why my answer is not same like you? Am I missing anything? 20,200 kilo is 10 power of 3, right? This one you got 3.982 times 10 power of 14, is it? Oh, I didn't square root the answer, sorry. So square root the answer. Yes. Yeah, yes. Okay, so 2,178.56 meter per second. Okay, sorry, I forgot to square root the answer. Okay, so you got the answer. Okay, so correct. Okay, so let's move on to the next one. So what will happen to the satellite if the linear speed of the satellite is less than the required of the linear speed? Okay, so if it less means, so if the linear speed is less than its required, so it will fall to a lower orbit. So it continue to revolve, okay, towards the earth until it enters the atmosphere. So the movement of the satellite at the high linear speed against air resistance will generate heat and eventually causes the satellite to burn. So let's say this is Earth. Okay, so let's say this is satellite. So if the linear speed is less than the required speed, okay, it will keep rotating, okay, until, okay, until it enter the atmosphere here. So when it enter the atmosphere, because of the air resistance, because of the air resistance is too high, okay, when it enter the atmosphere, okay, and you know the when the resistance, okay, it causes heat, right? Because we produce the heat, okay. So when it produce the heat, it will burn the satellite, okay. So that's what happened if the linear speed is not is low than required, okay. Okay, for the activity 3, okay, aim to compare between the geostationary and non-geostationary satellites. Okay, so what's the difference? Okay, for the geostationary satellite, so there are two kind of satellites. So the first one is a geostationary satellite and non-geostationary satellite. So the geostationary satellite is the satellite that move around the Earth at certain height, okay, in a special orbit named the geostationary Earth orbit. Okay, so it will rotate in a certain height. So this orbit, okay, this orbit that it used to rotate, we call it as a geostationary Earth orbit. Okay, move around the Earth in the same direction as the direction of the Earth rotation on its axis. So it will rotate in the same direction of the rotation of the Earth. Okay, so that's the characteristic of the geostationary satellite. Okay, and the orbital period, okay, is T is equals to 24 hours. So that is the same as the period of the rotation of the Earth. So one complete rotation of the Earth is actually equals to 24 hours, right? So the satellite also rotate with the same period. Okay. So when you complete, if you want to complete the orbital period, you want to complete the orbit, okay, it will complete in the time of 24 hours, same like the orbital period of the Earth. Okay, and always above the same geographical location. So let's say if you launch it from Malaysia, so means the satellite will stay, okay, at the same nation. So means it will always on the top of Malaysia. Okay, Malaysia like that. Okay, so it will always above the same geographical location. So this is the geostationary satellite. So how about non-geostationary satellite? So a satellite that move around the Earth at changing orbit height. So it's not constant. Okay. So the orbit may change. So normally in a lower or higher orbit than the geostationary Earth. So the geostationary Earth it constant. It has a constant orbit. Okay. It does not change the height of or change the orbit. But for non-geostationary satellite, it can move. Okay. It can move to the other orbit. Okay. So it's actually sometimes lower or higher. Okay, and the orbital period is shorter or longer than 24 hours. For geostationary satellite, to make one complete rotation, okay, it takes 24 hours. But for the non-geostationary satellite, is whether it's shorter or longer than 24 hours. Okay, and then another difference is it above the different geographical location at different time. Okay, so does not stay at the same place. Okay, so let's say the first time maybe at Malaysia, then maybe later it goes to the Philippines like that. So it will not stay at the same geographical location. Okay, so that's the difference between the geostationary satellite and also the non-geostationary satellite. Okay, so the similarity characteristic, so the orbit of the Earth, so you want to change, if you want to calculate the speed, okay, you can use the formula. Okay, this formula for the linear speed of the satellite. So for both geostationary satellite and non-geostationary satellite, if you want to calculate the speed, you can use this formula. Okay, and also for the orbital period, right? The orbital period for the satellite. Okay, so you can use this one, that is T is equals to square pi 4 pi square r cube over g m. Okay, so remember what is this is what law? Anyone still remember what law is this actually? It come from what law? Kepler's law. Okay, which part, which part of the Kepler's law? Law of what? Because we learned three laws, right? Yeah, the third law. So the third law is a law of period, right? The first law is a law of orbit. Okay, the second law is law of area, right? And then the third one is a law of period. Okay, right? So very good. So this is the difference. Okay. So the geostationary satellite, the direction of motion same as the direction of the Earth rotation. So let's say it move in the anti-clockwise, the Earth rotation is anti-clockwise, so it move at the same direction. It just follow the rotation of the Earth. Okay, for the non-geostationary satellite, the direction of motion need not be the same as the direction of the Earth rotation. So maybe let's say the Earth rotation is anti-clockwise. So it will move, it whether can move anti-clockwise also, or also it can move clockwise. Okay, so it can move with different direction as the Earth rotation. Okay, for the period for the geostationary satellite, okay, it's a constant, must be 24 hours to complete one complete circle. Okay, but for the non-geostationary satellite, is whether have to be shorter or longer. Okay, so maybe in less than 24 hours or maybe more than 24 hours for it to complete one rotation. Okay, one complete rotation. So for the position, the geostationary satellite is above the same geographical location. Okay, so I already told you, let's say we launch it from Malaysia, so it just will always on the top of Malaysia. It will not move to the other location. But for the non-geostationary satellite, so it can move to another location. So let's say for the first time maybe at Malaysia, the other will move to Indonesia like that. Okay, and the function, okay, for the geostationary satellite, we use it as the communication satellite, and for the non-geostationary satellite, we use the Earth imaging or GPS or weather or forecast. Okay, or weather forecast. Okay, so it's actually for GPS, Earth imaging. So of course you need to know, let's say just now, I think you already read, right, in the Facebook or in the news, okay, about the uh, ice, right? Ice cube, right? From the, I think for the North Pole, right? Okay. So it's like it's now already floating, right, to another part of the earth. I'm not sure where now. Okay, so that is how they can detect by using the Earth imaging. Okay, and the Miasat, so the geostationary satellite, okay, the example is Miasat. Okay, and for the non-geostationary satellite is a Teosat, Razaksat, Pipit, and ISS. Okay, so this one, the Teosat, Razaksat, this one is from Malaysia. Okay, so this is the example, the different characteristic between the geostationary satellite and non-geostationary satellite. Right, so any question you want to ask before I move on to the escape velocity? Okay. So the escape velocity. What does it mean by escape velocity? So escape velocity is the minimum velocity that needed by an object on the surface of the earth to overcome the gravitational force and escape to outer space. Okay, just now I think we already, not just now, I mean before this we learned, right? So we need a certain speed, okay? So let's say you want to launch a rocket. So you need the certain speed, okay, for the rocket to be launched at the outer space. Okay, if let's say it's lower than the that speed, okay, it will come back to the earth, right? So that velocity that needed, okay, so it can launch to the outer space, we call it as the escape velocity. Okay, so the escape velocity is the minimum velocity needed by an object on the surface of the earth to overcome the gravitational force and escape to the outer space. Okay, so if you want to launch a rocket, okay, so you need to know what the minimum velocity that it requires so it can be launched to the outer space. They say if less or more, okay, the rocket will come back to the earth. Okay, so that's the escape velocity. So when the escape velocity is achieved, okay, so when the minimum kinetic energy of an object is able to overcome the gravitational potential energy. So means you have to know what is the gravitational potential energy, and you already know the energy can change, right? So before, let's say the gravitational potential energy is actually is based on the height, right? So when and then when it launched, it changed to the kinetic energy. Okay, and you know that the conservation of energy said the energy cannot be destroyed, it only can change form. So the energy change from the gravitational potential energy to the kinetic energy. So when does the escape velocity is achieved? When the minimum kinetic energy of an object is able to overcome its gravitational potential energy. Okay. So this is the formula how we want to derive the escape velocity. So this one we already know. So let's say this is the object. Okay, so this is the gravitational force, gravitational potential energy. Okay, so the gravitational potential energy is based on the height. So when it launched, okay, it changed to the kinetic energy. Okay, so from here, okay, when it launch it's move, right? So when you move, any object that move must have the kinetic energy. So this gravitational potential energy, okay, will be equal as the kinetic energy because it's only can change form. Okay, that is the principal conservation of energy. So an example like this. Okay, so let's say if I have the U curve surface like this. So this is the object, this is the ball. Okay. So when the ball move from here to here, okay, it changed the energy. So this one you got the gravitational potential energy, right? So when you move down, the gravitational potential energy changed to kinetic energy. So at this part, the gravitational potential energy is equals to the kinetic energy. Okay, and then when you move up, okay, so this is the gravitational potential energy, right? So the kinetic energy will change to the gravitational potential energy. So when you move up, it will change. So when you reach at the top, okay, so the gravitational potential energy is actually equals back to the kinetic energy. Okay, so let's say this one, the gravitational potential energy is 20 joule. So when it reach here, is at this part, this is the maximum of the kinetic energy. So the kinetic energy here is also 20 joule. And we move here back, it will move up again. So this one, the gravitational potential energy is 20 joule. Okay, so means we know that from here, the energy is conserved. So that is the principal conservation of energy. So let's say this one also same. Okay, so when it has a certain height, okay, it consists of the gravitational potential energy. So when it start to move, the gravitational potential energy is changed to the kinetic energy, right? So when it's same, okay, when the kinetic energy and the gravitational potential energy is same, so this is the question for kinetic energy you already learned in form 3, okay, and this is the gravitational potential energy formula. So you must ask why there must be a negative, right? So the gravitational potential energy is actually acting toward the earth, okay, but the kinetic energy, it move, okay, it move outward, right? It move outward. It move in the opposite direction as the gravitational potential energy. So that's why you put a negative sign there. Okay. So this one because it move towards the earth and the kinetic energy it move opposite direction of the gravitational potential energy. So that's why you got the negative sign there. Okay. So after that we know that um, the minimum kinetic energy plus gravitational potential energy is 0. Okay. So it's actually like this. Okay. This one is if you follow the principal conservation of energy is actually like this. Okay. So when I move here, okay, so this one will become, wait, the minimum kinetic energy plus the gravitational potential energy is actually become 0. Okay, so when you plus this one, we move here, plus, right, you add these two, so positive, negative, so it become minus, right? Okay, so and then after that, if I change here, I move back to here, so it will become positive. So it should be like this. G M M over R. Okay. And then if I put like that, it have to be like this. Okay, G M M, okay, over R. Right, so this one I can cancel it. Okay, so it will be left by V square over 2 G M over R. So you just cross multiply again, G M 2. Okay, so if you want the escape velocity, so V square G M 2, okay, and divide by R. Okay, so V is actually equals to the square root 2 gm over R. So you got the answer, this velocity. So this is an escape velocity. So let's say if you want to keep the object keep rotating at the certain orbit and it will not fall to the earth, so you have to calculate this the speed, the minimum the escape velocity by using this formula. Okay, just now the linear speed is actually just to calculate the speed of the satellite, okay, when it already orbit the earth. Okay, but for this one, before we'll start to launch the rocket, we need to know first what is the escape velocity. Okay, so this is the escape velocity. So I hope you are not confusing with the first one. Okay, the first one, when the satellite is already orbit the earth. Okay, you already revolve around the earth, so you want to calculate the speed of the satellite when you already orbit the earth, so you use that formula. V is equals to gm over R, right? And then square root, but for this one is for the um, escape velocity. So what is the speed, okay, that you need before you launch the rocket? You need to know what is the velocity that you need to launch, okay, the rocket, so it can orbit in the certain it will rotate in the certain orbit and will not fall down back to the earth. Okay, so this is the formula. Okay, so can you calculate the escape velocity from the earth by using this formula? The formula is 2 gm over R square root. Am I correct? Wait, I check first the formula. Yes. 11.2 times 10 power of 3. Shwanki, can you put the answer in standard form? Because 11.2 you still can simplify it, right? Because if you want to put in the standard form, the value must from 1.1 until 9.9. Yes, 1.12 times 10 power of 4. Others? Why always same people give answer when others? Can you calculate or not actually? Chia Kai 1.12 times 10 power of 4. Okay, so let's check whether it's correct or not. Yes. So the answer is 1.12 times 10 power of 4. Okay, very good. Okay, so state the factor affecting the escape velocity. So the factor is actually you have to use the formula. So we use the formula that V is 2gm over r, right? So it's actually equals to the mass of the earth, the distance r, okay, and g is actually the constant value. Okay, so that one cannot be considered as the factor because it's a constant. Okay, and the mass of the earth also is a constant. So actually, the real factors that are affecting the escape velocity is the distance. Okay, the distance r of the object from the center of the earth. Okay, so this is the formula. Okay, so the benefits and the implication of escape velocity. Why the earth can maintain a layer of atmosphere around it, right? So the high escape velocity of the earth is 11,200. So this is the high escape velocity for the earth, 11,200 meter per second. So mean if you want to launch a rocket, so you have to make sure that the rocket can achieve like 11,200 meter per second. So then it can be launched to the outer space and will not come back to the earth. Okay, so the molecule of the atmosphere move at average of linear speed of 500 meter per second. So you can see it lower than the escape velocity. So when it lower than the escape velocity, so that's why it cannot escape to the outer space. So the air molecule will keep stay in the layer of the atmosphere. So because of the escape velocity is lower than the escape velocity of the earth. Okay, so the escape velocity because of the speed of the molecule, okay, when it move around the atmosphere is only 500. Okay, while the escape velocity of the earth is 11,000, so it's much lower. So when it lower, it cannot escape to the outer space, right? And why commercial aircraft cannot escape into the outer space. Okay, so for the commercial aircraft, so it can only fly at the 200 meter per second. Why you already know just now, the escape velocity for the earth is 11,200. Okay, but the aircraft can only fly at 250, so it's lower, right? So but the fighter jets, okay, that can achieve supersonic linear is only can travel 2,200 meter per second. So both are lower than the escape velocity for the earth. So that's why they cannot escape to the outer space. Okay, so how can a rocket achieve, okay, the escape velocity from the earth and send the spacecraft into outer space? Right, so the launching of rocket require large quantity of fuel. Okay, so when it burn, okay, that's why you can see there's a lot of hot air that coming out from the bottom of the rocket. Okay, so the launching of the rocket requires a large quantity of fuel, all right, to produce the high thrust that enable the rocket to achieve escape velocity of the earth. Okay, so means you have to know the means is required a lot of fuel. So when it burns a lot of fuels mean you have the high thrust of force. So this high thrust of force, okay, will able to overcome the escape velocity of the earth. So that's why it can be launched to the outer space. Okay, so it needs a lot of the kerosene. Okay, so that is actually the burning fuel that we use in the spacecraft. They use a kerosene, so you need a lot of the kerosene, okay, to be burned. Okay, so it can produce the large thrust force. So this large thrust force, okay, will produce a high velocity, okay, that can overcome the escape velocity of the earth and it can move to the outer space, right? So to solve problem involving escape velocity. So for the Venus, right? For the Venus, the escape velocity is 10,362, whilst the Mars is 5,018.9, and the Jupiter is 60,216.6. Okay, so this is actually you want to calculate, you can use this formula. So this is formula is actually not for only for the Earth. So it's actually you can use to the other planet also. Okay, and this for number two. Okay, so for number two, the moon and the sun are two bodies in the solar system. Okay, so this is the mass. Okay, this is the mass, this is the radius. Okay, so it's the moon and sun. Okay, for number one, you have to compare the gravitational acceleration on the moon and the sun. Okay, so I hope you can still remember how to calculate the gravitational acceleration. Okay, so can you try to calculate the gravitational acceleration? What is the formula? Can anyone give me the formula for the gravitational acceleration? What is the formula for the gravitational acceleration? Gm over r squared. Okay, so very good. Okay, can try to use that formula, okay, to calculate the gravitational acceleration. So for all the formula, I'm not sure whether they will give in the exam or not. Okay, so we have to see this year question first. What is the formula list? Okay, for this year of, okay, for this for SPM for this year. Okay, but I think at first maybe if we can go to school again and we have a exam, right? I think maybe I will give you at the first time because you are not familiar yet, right? Okay, and then after you calculate, you compare. Okay, so what I want you to give me the answer, you give me the answer for the gravitational acceleration of the moon, and then after that for the sun, and then you compare which one is much higher. So I'm sure you already remember the value of G is 6.67 times 10 power of negative 11. Okay, and then the mass also already been given and the radius also already been given. Did you get the answer for the gravitational acceleration? Moon 1.62 times 10 power of negative 10 and Sun is 274. Others 2.74 times 10 power of 2. Okay, so same as pi. Okay, so let's check the answer. The 1.62. For the moon, you got 1.62. Wait, let me check first whether the answer is wrong. 6.67 exponent negative 11 and 7.35 exponent 12. Then you divide by 1.74 exponent 6. Right. So the answer should be 1.62 times 10 power of negative 10. So here they're missing the times of 10 power of negative 10. Okay. So for the sun, yes, is correct. So if you want to compare, so means here the gravitational acceleration for the sun is much higher, right? So the escape, this is the escape velocity, okay? So the escape velocity for the moon is 2.37 times 10 power of 3. So this one we just use the formula. Okay, and the sun is 6.18 times 10 power of 5. So this one also, if you compare, you can see the escape velocity of the sun is higher, right? So why the moon has a low gravitational acceleration? For the first one is because of the mass. Okay, if you compare the mass of the moon and the sun, of course the mass of the moon is smaller than the sun. So that's why the gravitational acceleration also is smaller for the moon. Okay, and for the sun, okay, since it has the largest body in the solar system, so for the solar system, okay, the sun has the largest mass, right? So the gravitational acceleration on the sun and also the escape velocity from the sun have the highest value. Okay, so because of the mass, okay, of the mass, because of the mass of the moon. Okay, so discuss whether escape velocity from the Earth for spacecraft X of mass 1,500 kg is different from spacecraft of mass 2,000 kg. So is it different? Is it different if the spacecraft have the mass of the 1,500 and the spacecraft Y has the 2,000? Teacher, the moon, yes, the moon's mass should be 10 power of 12, not 12. Oh, for this one. The moon here is 12 power. Oh, yes. Thank you. Okay. But the answer is correct, is it? Let's try to calculate first. 6.67 exponent negative 11 times 7.35 exponent 12. Okay, and then you divide by 1.74 exponent 6, and then you square root the answer. 2.37. Can you calculate, because I think I got a different answer for this one. Maybe when I type it wrong. Yeah. Okay. and then divide 1.74 exponent 6, and then should see. I got 0.0237, so means 1 to 2.37, right? Supposedly. Times 10 power of 1, 2, 3. 2.37 times 10 power of 1, 2. 10 power of negative 2. So this is the answer. Can you make a correction here? This one is wrong. Okay. So for the sun is correct, right? For the sun, 2 times 6.67 exponent negative 11 times 1.99 exponent 30. 1.99 exponent 30. So divide by 6.96 exponent 8. And then you square root the answer. You got 6. Yes, well, this one is correct. Okay, only this one. Okay, so please make a correction. 2.37. Okay, so means the moon is much smaller. Okay, for the escape velocity, you only need like 0.0237 meter per second. Okay, alright. So this one discuss whether the escape velocity from the Earth from say spacecraft X of the mass 1,500 kg is different from spacecraft Y of mass of 2,000 kg. So means here they launch at Earth, but they have a different mass. So one is 1,500 and one is 2,000. Okay. So the escape velocity should be same because it only depends on the radius and also from the radius and also the mass of the Earth. Right. So it does not consider the mass of the spacecraft. So whether it's high or low, okay. So it will still have the same escape velocity. Okay, it only depend on the mass and also the radius of the Earth. So if you calculate, you will get like 11,200 right, meter per second. So that is the escape velocity for the Earth. Okay, so it doesn't the mass of the object that need to be launched, okay, is not influenced, okay, it's not influenced by the mass of the object. So only this depends on the mass of the Earth and also the radius. Okay, so let's calculate for this one. What is the linear speed for this satellite? So we use V is equals to G M over R, if I'm not mistaken. So this one. So this is the formula. G already given, the mass also already given, the radius of the Earth also already given. And also the height also already given. So this one should be R plus H. Seven thousand 504.82. Okay, meter per second. So correct. Okay, so we already finished for chapter 3. So after this, we go for chapter 4. Right? So I will discuss about 50 minutes. Okay, 50 minutes for the question on your online test. Okay. Okay, any question you want to ask before I stop for the chapter 3? And we move on to the discussion of the test. Because I see when I see your marks, okay, uh, um, not so many of you can get like, because for me, if you want to get the band 4 or band 5, at least you need to have like 7 70 something above. Okay, so if we get 70 above, then I can consider to give you whether band 4 or band 5. Okay, so it's okay. So let's see the question first. All right. So which of the following are derived and vector quantities? So what is a derived quantity? So derive, if you want to derive quantity, we use the base quantity, okay, and you use the multiplication or division, okay, or we use both, alright, and we can derive the derived quantity. So means it consists more than one base quantity. So let's say for the force, right? So what is the force? Force is F is equals to ma. Okay, so M is mass is kg, A is the acceleration, ms negative 2. So you can see here, it consists more than one base quantity. It consists kilogram, mass, and also second. So this is the force is a derived. But is it a vector quantity? Yes, force is a vector quantities. Example, the gravitational force. The gravitational force is always acting right towards the center of the earth. So it's got the direction. So means the force is also the vector quantity. Okay, how about the weight? Weight is also the derived quantity because weight is a Newton, right? And force is also Newton. Okay, so means is a derived quantity and weight also is a vector quantity because weight, you know, the gravitational pull the object towards the center. So the weight is always the direction is moved toward the center. So let's say this is you, right? So your weight is always in this direction. So it has a direction, it's a derived and also the vector. Okay, for the displacement, what's the unit for displacement? The unit for displacement is same as the length, right? The distance. So it's in meter. So mean is it a derived quantity? No, because it only consists one base quantity here, that is meter. So we didn't consider the displacement is a derived quantity, but it is a vector because displacement got the magnitude and also direction. Okay, so for this one, it must have both. Mean it must be a derived and it must be a vector quantity. So for A, it's wrong because of the displacement. Okay, and then for B, pressure, impulse, and velocity. Pressure is not the vector quantity. Okay, force divided, but it's not a derived quantity. Okay, so for B, of course, the answer is already wrong. Alright, and then for C, force, weight, and momentum. Force, we already know, yes, they are derived and also a vector. Weight, yes, they are derived and also a vector. Momentum, yes, right, it's also a derived and also a vector. Okay, so this one, the answer should be C. Okay, why the momentum is a vector? So this is the formula of momentum, right? So it use a velocity. The velocity has a direction, right? I already said if you want, if the velocity of the object is moved to the right, you consider it as a positive. But it move to the left, the V must be negative. So if you lazy the move to the left, so now the P will become the negative. So means it's a vector. Okay, so and also the derived, of course because P is mv, right? So mass is a kg, V is ms negative 1. The unit of the mass is kg, velocity is ms negative 1. So you can see here is a derived because it has a kilogram, have a mass, and mass has a second, so it consists more than one base quantity. So that's why we call it as a derived. So the answer should be C. Okay, so are you clear about number one? Okay, any question for number one? Okay, for number two, which of the following has the smallest value? So for this one, you have to change first to the standard form. Okay, and then you have to change the prefix. Okay, for this one is actually you already learned in form 1. Okay, but it will come out in the SPM too because for the SPM, the question come out from Form 1 until Form 5. It's same like maths also. Maths also we come up from Form 1 until Form 5. So same also like physics. So means you have to know, right? Because for Form 1 is actually you already learn some of the physics like force, okay, electricity. So that's one is actually from physics. So means you have to know the Ohm's law like that. So that's why you have to know. Okay. And for A, this one I changed, so it become 10 power of 1. Okay, and 10 power of 2. So this one is milli, right? So milli is 10 power of negative 3. Okay, so if I solve it 10 power of 3, so this one will be only left 2 meter. Okay, 1 plus 2 is 3, 3 minus 3 is 0. Okay, for B, so this one you have to change, right? 0.3 is actually 3.3 times 10 power of negative 1. Okay, I show you for B and you have to do on your own for C and D. Okay, and 10.3 power of 3 milli is 10 power of negative 3. So you have to remember the prefix. So negative 1 plus 3 is 2. 2 minus 3 you got 3 times 10 power of negative 1. Right, negative 1, 3, 2, 2, yes. Okay, and for C, right, for C and D please try to do, okay, based on the for A and B that I already teach you just now. For C and D, you have to calculate. Okay, we still have class on Thursday, right, for the tutorial. So for the tutorial, I will continue to discuss the question for this question. Okay, for the tutorial. So let's see if you want the PDF, okay, for the question here, you want a copy, you can text me. I will send the PDF to you. C is 5 times 10 power of negative 3. Right? So is it correct? 5 times 10 power of 6. Nano is 10 power of negative 9. Right? So 5 times 10 power of negative 3 meter. Okay, very good. Okay, how about D? For D is, what is a micro? Micro is 10 power of what? What is the prefix value for micro? This is actually the symbol for micro. 700. Okay, so let's say 7 times 10 power of 1. Okay, times 10 power of 7. Micro is 10 power of negative 6. Okay, so you will get 7 times 10 power of 2. So here you want the smallest value. So the smallest value is actually C, right? Okay, smallest value, so the answer should be C. Okay, for the last part, for the last question before I stop, okay, which of the following graph shows the relationship between the acceleration and the height for an object that undergoes the free fall? So what does it mean by free fall? What does it mean by free fall? What does it mean by free fall? Anyone still remember? We already learned in chapter 2, free fall. Yes, pulled by gravity only. Okay. So free fall means the object is fall under the force, under the gravitational force only. And you have to know the value of the acceleration. Okay, the value of the acceleration for the object is if it fall under the gravitational force only. So the acceleration also must be always same. Okay, so the answer should be A. Okay, so because it only here is the clue, free fall. Okay, free fall means the acceleration is only considered the gravitational force. Okay, so it fall only under the influence of the gravitational force. The gravitational force is 10 Newton, right? Okay, but for the acceleration, it will be always same. That is 9.81. Okay, so the answer should be A. But let's see if we give you the graph of the velocity against time. Okay, for V against time. So what is the graph that will that we produce if we change the graph to V against T? What is the relationship of the graph? Anyone? Let's say the question didn't give you the acceleration against height, they give you the velocity. So what is the direction? Yes, directly proportional. Very good. So the graph will be like this. So if you change to the acceleration, it will become like this because you know the gradient of the graph of velocity against time is actually the acceleration. Okay, so that's why you need to know. Okay, so I think I stop until here first. So I will continue for the tutorial. Okay, we will discuss for question number 4 until 36. Okay, so let's say if you want the copy of the PDS, please PM me. Okay, text me. I will send you through the WhatsApp. Right. So thank you, class. Right. So see you on Thursday. So if you have any question, you can text me. Right. So thank you for attending class. Right. Bye. Welcome. Yeah. You too. Stay safe.